Okay, this will be the lecture for Chapter 15, and we're going to start talking about some concepts of temperature, heat, and how these things can cause things to expand. And this kind of starts off the last little bit of Physics 101, which is going to be thermodynamics. Before I start talking about temperature, I just want to kind of come back to something we've already talked about a little bit, but kinetic molecular theory. And all matter is going to be made up of atoms and molecules that are in constant motion. And we've kind of said that the faster these atoms move, the hotter an object is going to become. So if you think about a proverbial solid right here, where we've got these atoms that are connected to one another by springs, and these guys are kind of vibrating back and forth like that. If we were to increase the kinetic or potential energy of any of these guys, what we're actually increasing is going to be the thermal energy. So if I said, okay, well, I'm going to add some energy to this guy, and rather than this thing bouncing back and forth with this much energy, now it's going to be bouncing back and forth with this much energy. It's got more kinetic energy, more potential energy, it has more thermal energy, and it's more likely to burn you. Now, when we talk about temperature, we're actually talking about a measurement of this thermal energy, or the sum of the kinetic and potential energies. One important thing about temperature is very typically we're used to working in the Fahrenheit scale right over here, where water freezes at 32 and it's going to boil at 212. And actually Leward Fahrenheit based the temperature scale off of his body temperature, so that's why body temperature is 98.6. It turns out that he was trying to call 100 the temperature of a human body, but he was running a fever that day. Now, all of these temperature scales are measures of thermal energy. It's just kind of, where do we put the tick marks on the ruler, if you will. But very typically in the SI system, we're going to work in the Celsius scale or the Kelvin scale, and I'll talk about those as we get deeper into temperature. But the Celsius scale makes a whole lot of sense because it's based off of the freezing and boiling points of water. Water is going to freeze at 0 degrees Celsius and it's going to boil at 100 degrees Celsius, and since most of the planet's made up of water, it makes a whole awful lot of sense. The Kelvin scale, we'll talk about that a little bit more in the next couple of chapters, but it has this thing called an absolute zero, which is going to be kind of like saying we have a temperature at which we can go no lower than. And if we think about that from a kinetic molecular point of view, that's going to be the point where an atom stops moving. So this creature called temperature is really just kind of putting a number that's going to correspond to the warmth or the coldness of an object, where these guys are really kind of talking about a measurement of thermal energy. Now, how we measure these guys, we measure them using a thermometer, and I'll talk about how a thermometer works in a little bit. And it's really kind of measuring the energy per particle. There is no upper limit on temperature. We can have temperatures that get hotter and hotter and hotter and hotter to infinity, if you will. But there is definitely a lower limit on temperature. And again, if you think about having some atoms in motion, so these guys are kind of going back and forth, there will be a point where these guys cannot move any longer, and that point is actually going to be 0 degrees Kelvin. And so there is a definite limit on the lower end of temperature, so kind of an important concept. Now, I did say on the last slide that temperature is kind of a per particle property, and what we're kind of measuring is going to be a kinetic energy or kinetic plus potential energy. Very typically we talk about gases or liquids, and when we talk about gases, it's going to be how fast the gas particle is going. We have a gas particle going some speed like that, then it's got some temperature. If we increase the temperature of the gas, then we're increasing its energy, so it's going to go faster. So this guy is going fast, this guy is going slow, so this guy is at a high temperature, this guy is at a low temperature. For liquids, it's how fast they slide and jiggle past each other. And for solids, it's how fast they move as they vibrate and wiggle back and forth. And if you think about it, this kind of makes sense if you have, just a solid. So I'm just going to draw a simple solid like this and say this guy is vibrating back and forth. And if we were to draw another solid and say this guy right here has got a much higher temperature, then if we're talking about like a piece of iron or something like that, and we touch a cold piece of iron, then it's not going to burn us. if we touch a hot piece of iron, this one down here, then it is going to burn us, essentially because this piece of iron is going to slam into our skin at a relatively fast speed, transferring a lot of energy to us. So how do we go ahead and measure temperature? Well, we could do it using what's called a thermometer, and there's two fairly basic types. There's going to be one of those IR thermometers, the one you kind of point at the wall and puts a laser on there, and essentially what it's doing is it's measuring the infrared radiation coming off that wall. And we'll talk about infrared radiation in the next couple of chapters. Let's just talk about a mercury thermometer, or an alcohol thermometer if you will. So kind of one of these guys with a bulb on the end, just like this. And so there's going to be usually some red mercury or alcohol in there. And what's going to happen is we're going to go ahead and we're going to stick this guy into our turkey. So this is going to be my turkey, and he's got some particles that are kind of wiggling back and forth. And what these guys kind of do is they wiggle and they bounce into the thermometer. And as they bounce into the thermometer, then they're going to transfer their energy. So right over here, the thermometer is going to start bouncing back and forth. And these guys are actually going to reach an equilibrium, which is kind of like saying they're going to bounce back and forth at the same rate. And what's going to happen is as these guys bounce back and forth, then this liquid is actually going to expand. So this guy is going to start to go like this, and suppose it goes into a hot turkey, then the liquid is going to expand up to here. And we can kind of put some tick marks on here, and we can label the tick marks whatever we want. If we want it in the Fahrenheit scale, it's in the Fahrenheit scale. If we want it in the Celsius scale, it's in the Celsius scale. And kind of the height that we read tells us this object's temperature, or how much energy it has. Now, something I talked about without really talking about on the last slide is going to be this transfer of thermal energy. We have a special name for that. That's called heat. So suppose I had a hot object right over here, and I put it right next to a cold object. Then what's going to happen is this hot object is going to have some particles that are going to essentially bounce into the cold object, and it's going to transfer some of the energy. So the energy is going to kind of go in this direction, and this transfer of energy is simply called heat, or heat flow. And this looks just an awful lot like work, and how that was the transfer of energy. Kind of think if I had a box right over here, and I went ahead and I lifted this box up to some height, then here it had some so here it had some potential energy. Right up here it had a much larger potential energy, and what I had to do is I had to do some work to it in order to increase that energy. Same is true for thermal energy. Heat is just the transfer of energy. One very, very, very important thing about heat, or heat flow, if you will, is going to be the direction that it flows. It will always, 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 always flow from hot to cold. It will never spontaneously flow from cold to hot. Now, let's just kind of think about what's going on. Suppose you have a piece of iron, like you have right over here, and you go ahead and you stick the hot end into the fire. Then if it's hotter, then these molecules are bouncing back and forth at a relatively large rate. And those molecules right there may bounce into this molecule right over here. It's going to transfer some energy to it. It's going to bounce into this one right here. It's going to bounce into this one right here. It's going to bounce into this one right here. And it's going to start transferring the energy, definitely from the hot end to the cold end. Why? Well, because the hot end is wiggling relatively fast, the cold end is wiggling relatively slow. Now, take just a second and pause it. Go ahead and think about the direction of heat flow from a hot thumbtack into some warm water. And the answer to this one is going to be B, from the hot thumbtack to the warm water. Yes, the water may be warm, but the thumbtack is red hot, and it will always be from the hotter object to the cooler object. Now, I do just want to get some terminology straight with you. If you have a hot potato, and this potato is really, 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 really hot, it does not possess heat. Heat is going to be the flow of energy. What this hot potato does possess is it's going to possess internal energy. It's going to have kinetic energy and potential energy, also called thermal energy, so there's going to be a lot of molecular motion. If we drop this potato into some cold water, then this creature called heat is going to flow, and the potato's internal energy is going to go down. So again, the hot potato does not possess heat. We're not going to have heat until there's a transfer of that energy. Now, when we do talk about heat, we are still talking about the transfer of energy, so it's going to have the same unit as energy, which is going to be a joule. And one thing that's kind of interesting is if you have a gram of water and you change its temperature by 1 degree Celsius, then we're actually going to call that 1 calorie. And when we talk about food calories, we're actually talking about kilocalories, so we're talking about 1,000 calories. And that's kind of the basis to where a calorie comes from. Now, to kind of go between joules and calorie, very typically we talk about energy in joules. 4.18 joules is going to be 1 calorie. So we could also say, it takes 4.18 joules to raise 1 gram of water by 1 degree Celsius. Now, one of the last pieces of jargon I want to get out of the way, it's going to be this concept of thermal equilibrium, and I've kind of already mentioned that before. If we have two objects and we're going to say they're going to be in thermal equilibrium, they're going to be in thermal equilibrium if there's going to be no heat flow between them, which is also going to happen when they're at the same temperature. So if you think, for example, if you had a 100 degree Celsius box right next to a 50 degree Celsius box, then these guys, there's going to be some heat flow. The molecules are going to be bumping into one another, and here we're going to have our heat flowing just like this. If we had a 200 degree Celsius boxes right next to each other, just like this, then these two are what we would say are in thermal equilibrium, because there's going to be no heat flow between the two of these guys, just like that. So same temperature or no heat flow, either one.